Good morning, everybody. Thank you for coming. I like to be at the history section because it's a well-known cognitive illusion that the human mind is focused too much on the present. And so we're all overestimating the current events, and that translates into physics in the sense that we are too much focused on what is happening today, this year, on big conferences, and we're not considering enough the history of physics and the long-term developments. So I would like to emphasize this important point of physics. And, well, my title is Why Minkowski Led Physics Astray, and I would like to jump into history in 1905 when Albert Einstein formulated the special theory of relativity. You all know about this. And it's important also the contribution of Henri Poincaré, which is sometimes a little bit neglected, but he made significant contributions to the special theory of relativity. And interestingly, if we look here at the details, Henri Poincaré was actually the first one who introduced something like a four-dimensional metric, and the first one who introduced the imaginary unit, who attached the imaginary unit to the time scale. And he had the idea of a four-dimensional reformulation of this mechanics. But, well, interestingly, he said, because in his opinion, the translation of physics into the language of four-dimensional geometry would entail too much effort for limited profit. That's Poincaré. And, but this point of view, this four-dimensional formulation has become very important and very influential. And Minkowski promoted it. And so we might ask, how did this happen, this really huge influence of Minkowski on the mindset of physicists? And actually it goes back to one famous presentation at the meeting of the Society of German Natural Scientists and Doctors in 1908. And you should know that it's the oldest scientific society in Germany, founded in 1822. And it had a very big reputation. And you see also the title is already something spectacular, two simple words, and it appears that a new era of physics opens. And of course, Minkowski was also from Göttingen, a famous mathematician with a famous tradition. And but if you look at the content, the equations of Newtonian mechanics are invariant in two senses. Firstly, their form is preserved when the underlying coordinate system undergoes any change. Secondly, by change in position and change in rotation. Secondly, by altering it in its state of motion, imposing some uniform translation on it. That's basically Lorentz invariance. Lorentz invariance is a remarkable property, but it's in that sense nothing new. And well, Minkowski postulated what he said: 300,000 meters per second is 1 second. In the imaginary unit, that's basically setting the speed of light equal to 1. That was his idea, and he called that world postulate. And that's how he commented. The unquestionable validity of the world postulate is the essence of an electromagnetic world picture invented by Lorentz, further developed by Einstein, that has now become obvious. That's not a too modest statement, is it? As the mathematical consequences evolve, those who are reluctant will find relief in the idea of a pre-established harmony between pure mathematics and physics. So one might wonder about the relation of physical content and public relations, and it's formulated in a very poetic language. Let's see if I can go back this. I think I skipped that before, but he phrased his findings in a very poetic language. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. And all this is nothing else but, well, stating that there is Lorentz invariance, if you want to look at it soberly. So, I think, I mean, considering the huge influence of Minkowski in today's thinking, in today's paradigms of theoretical physics, we are well advised to wonder about the content of poetry and the real physical content in his findings. And that's his statement of the new era. And of course, he came from a famous tradition in Göttingen. Göttingen was the university of the most famous mathematicians, David Hilbert and Felix Klein and Hermann Minkowski. And also there, I don't want to give all the blame to Minkowski, but also there was the origin of the idea that further progress in physics could only be established by, well, inventing new mathematics and by considering purely mathematical relations, which I think is at the long run misguided. But everyone talks about Minkowski's space-time. It's really at the very basic education level in special relativity, as it was a necessary part. And Julian, yeah, I mean, just to summarize the findings, I mean, what he did, I mean, he did reveal some mathematical properties which are intriguing of special relativity, such as the four-dimensional distance and the negative distances interpreted in the generalized rotations, that Lorentz boost can be seen as a rotation in four-dimensional space. That's all very nice in the concept of a light cone. His ideas had an enormous influence on the paradigm of theoretical physics, and they are seen as an essential element of special relativity and also general relativity. I would like to question that, and of course Minkowski's influence was also that he encouraged physicists to think in higher dimensional spaces. That was the first step from 3 dimensions of reality to that 4th dimension. And I'd like to quote the historian physicist Julian Barbour, the author of the book The End of Time, and he correctly noted Hermann Minkowski's ideas have penetrated deep into the psyche of modern physicists. I would like to add, maybe by bypassing reason a little bit, because it's not, if you take a sober look at the facts, it's not really new content what Minkowski had developed. And even Einstein was a little bit reluctant. He ironically commented, since the mathematicians have invaded the theory of relativity, I do not understand it myself anymore. But that was a little comment, but Einstein did not actively oppose to the 4-dimensional formulation of this theory. And well, what's physics? Physics is about pondering deep concepts. Nothing is created by coincidence, rather there is reason and necessity for everything, as the ancient philosophers said. And I think we have to ask the basic questions, and one of the basic questions is, how justified is this union of 3-dimensional space and 1-dimensional time? And it turns out that there is no real justification besides that that postulate by Minkowski, I mean, space and time are simply different phenomenologies of physics, and gluing them to a four-dimensional space-time is, well, at the very end, nothing but a denial of reality. Okay? Just lean back and think about, is space and time really the same thing? It's not. But this argument, I mean, it's this central argument of mine, it is so simple that you might easily dismiss it and say, okay, if it's such a simple thing, why haven't physicists thought about for 100 years? But on the other hand, I think it's precisely the problem of theoretical physics for almost 1 century that it has given up pondering deep physical concept in favor of playing with mathematical formulations. Okay? And this is an unsolved problem. It's still on the table. There is no reason why nature should show its four dimensions in such a peculiar 3 + 1 dimensional manner. There is no mathematical reason. Okay? So you can't just treat it as something four-dimensional and say, okay, there is a little conversion factor, don't mind, we don't worry about. And I also think that strips off, that kind of thinking strips off the fundamental meaning of the speed of light, because the very existence of the speed of light tells us something about reality. Okay? There is no a priori reason why something as a limiting velocity should exist in nature, and people should wonder about these concepts. And I think Minkowski's paradigm was, well, helped a little bit to dismiss and to belittle the importance of this speed of light. So one of my favorite quotes of Erwin Schrödinger, and a little bit another context: once a problem is removed by a feeble excuse, there is no further need to ponder over it. And so now let's continue history. Einstein, after having formulated special relativity in 1905, continued with general relativity. And you might think, well, general relativity is 1915. No, the very first idea about general relativity, the key idea, so to speak, was the principle of equivalence in 1907. And he developed the idea that light should be deflected in a gravitational field as it is obviously deflected in an accelerating frame. And that was 1907. And another, interestingly, the immediate idea of how to resolve that, how could possibly a gravity field, how could it possibly bend light, was, okay, let's think about a variable speed of light. Let's think about a refractive index like in optics. And that's what Einstein published in 1911. And this is strictly speaking not related to Minkowski, but it's a very interesting formulation of general relativity, which I think could have more importance. But I mean, if you take the mindset of Minkowski and that four-dimensional formalism, you're not thinking in this terms of variable speed of light. It's a little bit two different paths that had opened back then, one formalistic mathematical formulation and the other one more intuitive of variable speed of light. That's what Einstein said in Prague. From the just proved assertion that the speed of light is in a gravity field is a function of position, it is easily deduced from Huygens' principle that light rays propagating at right angles to the gravity field must experience curvature. And interestingly, Einstein's idea included Mach's principle. He would have been thrilled had he known about the size of the universe back then. It was 1911. Just remember that the size of the universe was discovered around 1930. And Ernst Mach was also a profound thinker of gravity, and I think in a certain sense you could see in him an antipode to Minkowski. Minkowski represented the mathematical formulations in 4 dimensions, and Mach, maybe he was not such a brilliant mathematician, but he had very relevant ideas about the origin of inertia and the origin of gravity, which I think are underestimated to this day. And so, but yeah, maybe just history took the wrong path back then. I have other talks about this theory of Einstein in 1911, which was the first variable speed of light formulation of general relativity. There is also a very interesting relation to Dirac's large numbers, which I'm not going to mention in detail now. And however, all this is a quite interesting picture, not only historically, because all these people had very ideas that are very close together. Erwin Schrödinger's thoughts about cosmology, Dirac's large numbers, Mach's principle, Einstein's variable speed of light approach, which was rediscovered by a British cosmologist later, and first of all, maybe Robert Dicke. He also had a variable speed of light formulation. I think this is a very underestimated possibility how one could formulate general relativity, but it's very contrary to the 4-dimensional paradigm which had been established long before. So, I mean, Minkowski is not the only guilty one. Einstein got in contact with Marcel Grossmann and learned the geometry of Bernhard Riemann from Marcel Grossmann when he moved from Prague to Zurich in 1911. And so he started to look closer at this geometrical formulation, which you can do, of course, but it's just 2 sides of a medal. You can either formulate it with metrics and connections and curvature, or you can formulate it with variable speed of light. And this is not well known, and you might look at this statement of Einstein in 1913. The speed of light is no constant but depends on position. Therefore, one is forced to generalize the theory of space and time known as relativity. And so you might think that he gave up this variable speed of light thoughts in 1915 when he came up with the tensor equations of general relativity in Schwarzschild's solution. But look at this. In 1917, a curvature of light rays can only occur when the velocity of light varies with position. So Einstein obviously did not dismiss this variable speed of light point of view. So even if he became famous in 1919 when Eddington presented his legendary results from the excursion and at the Royal Society in London, New York Times headline the next day is "Big Revolution in Physics in 1919. Newton is dead, we have a new hero, Einstein." And this was the moment where the geometric formulation was really established. And you might think, well, Einstein gave it up later. No, in 1920 he still wrote about the other possibility. This consequence shows that the law of constancy of the speed of light no longer holds according to the general theory of relativity in spaces that have gravitational fields. This is 1920, okay? And he continues, as a simple geometric consideration shows, the curvature of light rays occurs only in spaces where the speed of light is spatially variable. From this it follows that the entire conceptual system of the theory of special relativity can claim rigorous validity only for those space-time domains where gravitational fields are absent. Okay, so this is just a small summary of this variable speed of light version of general relativity, which is in contrast to the Minkowski point of view. Variable speed of light was Einstein's initial idea in 1907. It's determined by the distribution of masses in the universe. That's the very Machian idea behind. The change of t is hidden by the simultaneous contraction of measuring rods. Of course, you always measure this very same velocity of light, because if the speed of light changes, the wavelength and the frequencies change accordingly, so that you can even define, as it is done today, c as a constant. Very interestingly, it's just an elimination of the gravitational constant by construction. It agrees with Dirac hypothesis, and there are interesting cosmological differences, which I'm not going to deepen today. Let's get back to Minkowski. Did Minkowski's concept really help to develop general relativity? I think no. The four-dimensional formulation rather obfuscates the variable speed of light concept. There is another line of argument I'd like to briefly touch. I think physics does not wander enough about fundamental constants, about constants of nature. And you have an interesting statement, a later statement of Einstein here. Numbers arbitrarily chosen by God do not exist, and their alleged existence relies on our incomplete understanding. I like this statement because it emphasizes that you shouldn't take constants for nature, you shouldn't take them for granted. You shouldn't just believe them as God-given numbers and work with them. You should ponder and stop and explain their very existence sometimes. So there is another talk on Thursday about constants of nature, the Royal Road to Fundamental Physics, where I would like to deepen this, but I can briefly lay out the idea. If you look at history and look at scientific revolutions, what's the first step? The first step is not mathematics. The first step is always a visionary idea, and then in the second step you have a mathematization, you have an important equation, and in the end you have always a reduction of the number of constants of nature. Now this sounds quite abstract. I give you 3 examples. Take Newton's law of gravitation. Okay, you have this inverse squared law, which is fantastic and worked out in decades of mathematical pondering, but the very revolutionary idea is the first one. Mundane and celestial gravity have the same origin. That's the unifying concept. It sounds very simple to us today, but in 1687 it was not. And if you look what happens then, I mean, think at the time before Newton, if you measure local gravity, okay, how fast things are accelerated, this could be considered an important constant of nature. That tells you something about nature, how fast, how strong gravity is, okay? But once you have understood Newton's law of gravitation, this little g, this local acceleration, becomes totally irrelevant. So it's one just on a little planet, and it depends on the mass of this little planet and the distance and of this universal constant. But this is the important constant. This has become irrelevant. This has become eliminated by that equation. Another example, entirely different field, look at electrodynamics. But what's the big revolution? The big revolution is, oh wow, light is an electromagnetic wave. Okay? That was, by the way, the first idea by Weber. And then came Maxwell, and of course he had the formulation, the mathematical formulation with Maxwell's equations, eventually coming out with this very, very important relation that says, okay, we have electricity, we can measure it, we can measure magnetic constants, and we have the speed of light, and these are related. Okay? And the essence of the revolution stays in the fact that you're eliminating one constant of nature here. You had three constants of nature independently, if you don't understand the connection. And once you understood that light is an electromagnetic wave, you have only two. That's the big progress. Again, another field, thermodynamics, and well, the revolutionary idea of Mach was temperature is nothing else but kinetic energy. Okay? So have a little mathematization and look at this. I mean, this could be considered an important constant of nature, later called Boltzmann's constant. But once you understand, so it becomes a totally irrelevant number that defines just the temperature scale. Okay? So my point of view is when you have revolutions in physics, look at the constants of nature, and in every revolution there is a reduction of the number of fundamental constants. And well, did Minkowski explain the existence of for C or even a finite C? No, he did not. To the contrary, his views help to dismiss the fundamental importance, because if you look at the history of physics in this way, you end up at the very end with questioning or wondering about the very existence of C. Why is nature built in such a way that you have certain constants that you can't get rid of? We have been able to get rid of a couple of constants, epsilon 0 and so on, and Boltzmann's constants, but there are some constants still remaining. But I think if we want to do real progress, we have to eliminate or to explain these remaining constants. One of them is C. And this is again touching another talk of mine on Friday. Every constant of nature is something like an anomaly in a sense of the science philosopher Thomas Kuhn. He said, whenever an anomaly appears, that means something is wrong. And I think at a very long time scale, we are talking about 400 years, you could look at the velocity of light as an anomaly. There is no reason whatsoever from Newtonian physics that tells you that accelerated masses should have a limited velocity. Why? There's just no reason. So if we stumble upon an anomaly, we shouldn't just declare it irrelevant and the constant of nature and digest it. We should ponder it and ask for the reason of the very existence, and at the very end that casts doubt on the very concept of space and time. More on that on Friday. And well, to conclude, is the book of nature written in mathematical language? Yes and no. I mean, I think that today there are obvious degenerations of science, like conferences taking place a couple of years ago here in Munich, scientific methodology in the absence of empirical data. That basically means scientific methodology without science. I mean, that to me is kind of obviously ridiculous. And you can you can just randomly pick out one of these 10,000 papers and multi-Galileons and higher codimensional brains and 5-dimensional bulk with Lovelock terms and 3-brain and so forth. I mean, you know, I just picked this out because it's kind of funny, because they refer to Galileo. I mean, they are inventing all kinds of particles, but they are referring to Galileo. And Galileo said, I don't feel obliged to believe that the same God who has endowed us with sense, reason, and intellect is intended to forego their use. But that's just a sideline. I'm going to finish. Is the book written in mathematical language? Yes, I'm not arguing against this. I think there are very interesting things. And, well, to conclude, for the space-time, that's basically all what I said. There is no good reason for why nature should behave in such a peculiar three-dimensional manner. I think we should ponder that. And you find more about these ideas in this publication in Annalen der Physik. I developed the Machian version of Einstein's relativity. This is about the origin of constants C and H. And this is a popular book about the fundamentals of physics. There is also a YouTube channel. And this is maybe the closest book to the ideas I was presenting today, Einstein's Lost Key, Why We Overlooked the Best Idea of the 20th Century. I think that Minkowski has contributed a little bit that physics has gone off the rails. Thank you for your patience, and I'm happy to have some questions.